Hello there, welcome to section 2 of unit 4. In this section, we'll be looking at adiabatic changes. Let's go through the objectives of this section. At the end of this section, you should be able to define what an adiabatic process is, sketch the PV diagram of an adiabatic expansion, and lastly, you should be able to derive an equation for pressure and volume for an ideal gas. Let's look at adiabatic process. We can explain adiabatic process as one in which no energy is exchanged by heat between the system and its surroundings or environment. Because there is no change in energy or no transfer of energy between the system and its environment, we can represent our Q to be equal to what? 0. And from our first law of thermodynamics, we know that internal energy is equal to what? Heat. That's energy minus what? Work done. But this time around, we have our energy here to be equal to 0. So that our internal energy now becomes negative W. That's the negative of work done. Let's look at some expressions here. Let the infinitesimal change in the volume to be dV and the infinitesimal change in temperature to be what? dT. Our work done can be expressed as P dV. Let me go a little bit backwards and explain how we had pressure times the infinitesimal change in volume here. We know that our work done from our previous unit and sessions is always equal to what? Force times distance, right? And also, we know that pressure is always equal to force over area. Making force the subject, it means you are going to get pressure times area times this d, the distance here. Because we have area here and we have a d here, we can combine the two to get what? A volume. So that at the end, we get our work done here to be equal to what? P, that's our pressure volume. But this time around, we know that our V here is infinitesimal change in volume. So we bring our D here. Now, we can express our internal energy as N CV. The V here should be small letter. It's a subscript actually. CV dt equals the work done, which is negative P dV. In making dt the subject, we are to get negative P dV all over N CV. Taking the total differential of the equation of the state of an ideal gas, PV equals nRT, it means we are going to differentiate through so that we get P dV plus V dP equals nR dt. Now let's eliminate dt by bringing the dt that we already expressed in the previous slide in this equation or expression. We are also able to find out that in our molar specific heat capacity for constant pressure and volume, we had R to be equal to Cp minus Cv. And we also divide the PV throughout this expression. So from what we had earlier for the R, when we divide the molar specific heat capacity of at constant pressure and at constant volume, let's represent it with gamma. After dividing through by PV, we are supposed to get, because PV is going to come here, PV will come here, PV will be divided here, so that the P here will be cancelled the P here and we'll be left with V here. And the V here will cancel this V and it will let it P here. And the last one there, P here will cancel the P here and it will be left with a V, this one. And already we know that R here is equal to what? CP minus CV, which we will replace it here. So that at the end, we'll be getting dV over V plus dP over P to be equal to the negative of all into bracket Cp minus Cv all divided by Cv, bracket close, dV over V. And this whole expression, right now this is the expression we've reached. This whole expression, and taking only this part of the expression, we can represent it by 1 minus gamma, or in a bracket, dV over V. Because we already know that gamma is what? Cp over Cv. So that at the end, we will get our final expression to be the dP over P that we have here. Let me use the laser pointer. The dP over P that we have here, right here, and we already have a dV over V. So that at the end, we get what? A plus of gamma dV over V equals what? 0. Because you have to expatiate this one. You get another dV over V here. Then you send it to the other side. It will cancel out and it will be left with only gamma dV over V. So when you integrate this whole expression at the end, and we get this differentiation expression, we integrate this one into the natural logarithm. We are going to get the in of P plus gamma in of V equals what? A constant, which can be expressed as PV raised to the power gamma to be equals to what? A constant. We already know from our ideal gas equation that PV is equal to what? nRT over V. Sorry, nRT. So we can represent P as this whole thing that we have here and bring our V here too, so that it will multiply this particular V and we get what? Equals a constant. On this PV diagram, such as the one that we've displayed here, the process occurs along a line called the adiabat that has an equation of P equals a constant over V raised to the power gamma. Since the gas goes from the initial state I to final F, we have Pi and Pv, Vi and Vf, and Ti and Tf. Where this time around, we have the Tf to be less than what? Ti. So that at the end, we can write an expression as Pi Vi all raised to the power gamma equals Pf Vf all raised to the power gamma. From the same expression that we derived earlier, that's into bracket nRT over V, bracket close, multiplying V raised to the power gamma equals a constant. Because n and r are constant, we can also write an alternative form. That's Tv raised to the power gamma minus 1 equals a constant, which when the gas goes from I to the final of our variable or a constant, we can say Ti Vi raised to the power gamma minus 1 equals Tf Vf raised to the power gamma minus 1.